Welcome back to Enzyme Kinetics, parameters of enzyme activity. This time, we will see how the Michaelis-Menten equation can be derived, the assumptions that are made along the way, and graphical solutions of the equation. To get the most out of the videos, I recommend watching them in order. This is a reminder that this presentation is Dr. Johnson's intellectual property. Enzymatic reactions, when plotted with the initial reaction rate as a function of substrate concentration, often give us a reaction curve that looks like this. The rate is proportional to substrate at low concentrations, but independent of substrate at high concentrations. This behavior is not entirely consistent with a first-order reaction. Since the difference is due to the presence of enzyme must be involved in the reaction and therefore the reaction kinetics. This diagram is one way to express the interaction of the substrate with the enzyme. Substrate binds to the enzyme, forms an ES complex, which undergoes a chemical conversion to the EP complex, and then product is released from the enzyme, leaving the enzyme ready to catalyze another round of reaction. So now we have a problem. How can we figure out the kinetic constants from this? In 1902, Adrian J. Brown proposed a simple model to explain the substrate dependence of the enzyme catalyzed reaction using a single substrate and product. In order to use Brown's view of the reaction, it needed to be described mathematically. This was first done in 1903 by Victor Henry and then again in 1913 by Leonor Michaelis and Maud Menten. The full set of steps for a single substrate, single product reaction involving an enzyme can also be shown in this way. Here we are considering that each of the steps is reversible, and we are showing the rates of reaction for each step in both directions. So K1 is the rate in the forward direction, and K-1 is the rate in the reverse direction. While this is the most complete way of thinking about the kinetics of an enzyme-catalyzed reaction, it is more complex than necessary. Let's see how we can simplify this expression. In most, but not all, enzymatic reactions, formation of the ES complex is fast. The conversion of the ES complex to the EP complex is normally the slowest or rate-determining step of the reaction. The release of the product from the enzyme is, like formation of the ES complex, normally fast. We know from physical chemistry that any steps after the slowest step of the reaction do not affect the overall rate of reaction, so we don't need to consider release of the product. We also know that all steps leading up to the rate-determining step do factor into the rate expression. Furthermore, we normally set up reactions so that they are under conditions in which the reverse reaction of EP becoming ES is negligible, and we measure the initial rate of reaction where the reverse reaction is insignificant. Therefore, we can simplify the reaction to this one. Out of this view of the reaction, we get two important expressions. First, the rate of reaction is the change of P as a function of the change in time. Another way to look at this is that the rate of formation of P is a function of the rate of conversion of the ES complex to product and the concentration of the ES complex. Secondly, we can see that the concentration of the ES complex at any time comes from the formation of the ES complex and the degradation of this complex, either from dissociation or reaction. In order to go on from here, we need to make some assumptions. First, we make the assumption that formation of the ES complex is readily reversible, that is, it is under equilibrium. We can express this equilibrium with the term Ks. The implication of this assumption is that there is a low energy barrier to formation of the complex. It is important to recognize that this is only true under particular circumstances, such as K2 being much slower than K-1. Secondly, we need to make the assumption that the concentration of ES does not change appreciably for most of the reaction. This assumption, first proposed in 1925 by Briggs and Haldane, is known as the steady state assumption. This is vitally important because it means that the change in ES concentration is zero and allows us to replace this term in the kinetic expression. There is one other piece of information that we need relating to the ES concentration, and this is that we know the total amount of enzyme in the reaction. This is the same as the initial amount we added. It does not change over the course of the reaction, although its form, free or in the ES complex, does. Since we know the total enzyme and use ES in the kinetic expression, normally we will rearrange this expression for free enzyme. Our next step is to put these together with the expression for the change in the ES concentration from the previous slide. What you see here is a derivation of the Michaelis-Menten equation. There are a number of different ways to approach this. I'm showing you the way I learned it. We start with the expression for the change in ES concentration as a function of time and apply the steady state assumption that this change is zero for the time of the reaction that we will be measuring. At the same time, we will also replace the term for free enzyme. Then we add this term for the disappearance of the ES complex to both sides of the equation. The right-hand side of the equation can be expanded by multiplying out all of the terms. Now we can move all the ES factors to the left side of the equation. Solving for ES gives us this equation with all the kinetic constants. We can simplify this by dividing top and bottom of the right side by K1. The rate constants are now all grouped together. We can define this relationship of the rate constants as Km, the Michaelis constant. The equation looks much easier when Km is substituted into it. So now we have an expression for ES in terms that are all measurable. This needs to be inserted into the rate expression for the reaction. You may recall this expression for the rate of enzymatic reaction. We left off with it earlier because we did not have a solution for the ES concentration. Now that we do, we will substitute this into the rate expression. This equation now has the form of the familiar Michaelis-Menten equation. The final step is to realize that at high substrate concentration, we have reached maximal velocity, so Vmax is determined by the rate of product formation from the ES complex and the total enzyme concentration. We can measure Vmax, so we will substitute this into the equation. This is now the normal form of the Michaelis-Menten equation. The Michaelis-Menten equation describes the first-order behavior observed at low substrate concentrations and the pseudo-zero-order behavior observed at high substrate concentrations. Vmax is the rate observed when the enzyme is saturated with substrate. The substrate concentration that gives half Vmax is the Km. There are two limiting cases arising from the Michaelis-Menten equation. First, at very low substrate concentrations, where Km is much greater than the substrate concentration, we can ignore the substrate concentration in the denominator of the equation, and it reduces to Kcat Es over Km. This describes the pseudo first-order kinetics region near the origin because the amount of enzyme used in the assays must be constant. The second occurs at very high substrate concentrations, where substrate is much greater than Km. In this case, the denominator of the equation is almost the same as the substrate concentration. Now, V0 is Kcat E. This describes the pseudo-zero-order kinetics seen under these conditions, where the enzyme is saturated. The rate observed under these conditions is Vmax. There are at least 4 different ways that the rates we measure can be plotted. A direct or Michaelis plot of V0 as a function of S gives us the hyperbolic curve we are familiar with. If we use curve fitting software, we can determine the Vmax value. Km occurs at half Vmax. Most enzymologists today use this type of plot and curve fitting software to determine kinetic constants. The double reciprocal Lineweaver-Burke plot is a linear representation of the data. This is the most common, but is quite error-prone because it places undue emphasis on the points with the lowest substrate concentrations. In this plot, the y-intercept gives us the value for the inverse of Vmax. The x-intercept, being negative, gives us -1 over Km. Because this plot has been used for a long time, it is great for illustrative purposes. In the Haynes-Wolff plot, S over V0 is plotted as a function of S. The y-intercept is Km over Vmax, and the x-intercept is -1 over Km. This is arguably the most accurate of the plots I'm showing you here, but is not used very often. The Eadie-Hofstee plot is V0 plotted as a function of V0 over S. Here, the y-intercept is Vmax, the slope is -Km, and the x-intercept is Vmax over Km. While this plot is considered to be more accurate than the Lineweaver-Burke plot, it tends to make even good data look worse. Before we leave this section of enzyme kinetics, let's have a little look at history. While Leonor Michaelis was based in Germany at the time of the Michaelis-Menten equation, Maud Menten had Canadian roots. She was born in Port Lambton, Ontario, and studied medicine at the University of Toronto, graduating in 1911. Because women were not allowed to pursue doctoral degrees at the university at that time, she moved to Berlin for her PhD, where she studied with Michaelis, graduating in 1916. Her work after returning to North America was in pathology. Michaelis and Menten's work grew out of the ideas of other scientists, notably Brown and Henry. Their paper, published in 1913 in the Biochemische Zeitschrift, has been translated into English and is regarded as the seminal paper on enzyme kinetics because they were the first to provide an experimental approach using initial reaction rates and controlling pH. The actual form of the Michaelis-Menten equation is the same as the equation proposed by Victor Henry. Next time, we'll discuss the kinetic constants.